Hi everyone, welcome to the lecture series of Abstract Algebra, part 1 of Module 2. It's me, Dr. Shahida AT, Assistant Professor, MES Mampad College. For reference, we can use the book A First Course in Abstract Algebra by John B. Fraley. The previous module, that is Module 1, we already discussed about what is a group, subgroup, related properties, and some theorems. So in this session, that is the part 1 of Module 2, we are going to discuss about cyclic groups and subgroup and some examples. First one is a theorem. Let G be a group and let A belongs to G. Then H is equal to set of all A raised to n is an integer, is a subgroup of G and is the smallest subgroup of G that contains A. That is, every subgroup containing A contains H. That is, we want to prove that if we consider the subset H is equal to set of all A power A, an integer, is a subgroup of G, where A is an element of G, where n may be any integer means n may be negative, positive or 0. Now we want to prove that the subset H of G is a subgroup of G. First we want to prove H is closed under the binary operation of G. For that, if we consider two elements A raised to n and A raised to m belongs to H, then A raised to n into A raised to m is equal to A raised to n plus m. Since n plus 1 is again an integer, A raised to n plus 1 belongs to H. Therefore, H is closed under the binary operation of G. Now, putting A raised to 0 is the identity, then E can be represented as the power of A. Therefore, E belongs to H. Therefore, the identity element belongs to H. Now, we want to prove that every element of H has inverse in H. If we consider the element A raised to n belongs to H, n is an integer, minus n is also an integer. Therefore, A raised to minus n also belongs to H. Taking the product of A raised to n and A raised to minus 1, we get A raised to 0, that's equal to the identity. Means that A raised to n into A raised to minus n is equal to identity. Therefore, every element of H has inverse in H. Hence, H is a subgroup of G. The subgroup we just discussed in the previous theorem is called a cyclic subgroup of G generated by the element E and is denoted by cyclic A. That is, the definition of cyclic subgroup is, let G be a group and let A belongs to G, then the subgroup H is equal to set of all or A raised to n is an integer of G is called the cyclic subgroup of G generated by A and is denoted by cyclic A. If the cyclic subgroup is finite, then the order of the smallest positive integer m such that A raised to m is equal to E. In this case, we write order of A is equal to m. If the cyclic subgroup A is infinite, then A is of infinite order. In this case of addition, that is, if we consider the addition modulo or the set of all integers under addition, we are consider A raised to n as n times A, that n plus etc. n times A. Example. This is an example of a cyclic subgroup. Consider Z6, set 0, 1, 2, 3, 4, 5 is a group with respect to the composition addition modulo 6. Now we are discussing about the cyclic subgroup of Z6. First we take the element 0. Then here cyclic 0 contain only one element, therefore order of cyclic 0 is equal to 1. Second subgroup is cyclic 1. Cyclic 1 means using 1 we can consider all the powers of 1. 1 raised to 1, 1 square, 1 cube, 1 raised to 4, 1 raised to 5 and last one is 1 raised to 6. That is, here addition is the binary operation 1 comma 1 raised to 2 means 1 plus 1, that is 2. 1 plus 1 raised to 1 cube is equal to 1 plus 1 plus 1, that's equal to 3. Likewise, 1 raised to 6 is equal to 1 plus etc. 1 6 times, that's equal to 6. 6 means 0 in Z6. Therefore, we get cyclic 6 is equal to Z6 itself. Therefore, order of the cyclic subgroup is equal to 6. Cyclic 2 means consider the powers of 2, that is 2, 2 raised to 2, 2 cube etc. So here 2 raised to 1 is equal to 2. 2 square is equal to 2 plus 2 is equal to 4. 2 raised to 3 is equal to 2 plus 2 plus 2 is equal to 6. 6 is equal to 0. Therefore, cyclic 2 is equal to 0, 2, 4. And the order of this group is subgroup is 3. Similarly, cyclic 3 is equal to 3 comma 3 square, that is 6, 0. Therefore, cyclic 3 is equal to this set 0 comma 3. Therefore, order of 3 is equal to 2. Next one, cyclic 4 is equal to 4 comma 4 square 4 cube. So 4 itself. Then 4 square is equal to 4 plus 4 is equal to 8. That is the remainder 2 under addition modulo 6. Therefore, the element is 2. And 4 plus 4 plus 4 is equal to 12. Divided by 6, the remainder is 0. Therefore, we get the cyclic 4 is equal to this set 0 to 4. Therefore, order of cyclic 4 is equal to 3. Also consider cyclic 5. That we get Z6 itself. So here all the subgroups are finite. Actually, the group itself finite. Therefore, we get only finite subgroups. Here, two cyclic subgroups are equal to the set Z6. That is cyclic 1 and cyclic 5. Example 2. Consider the group Z of all integers under addition. That is Z, plus. Binary operation plus. Where Z means the set of all integers etc. minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. If we take the cyclic 3, we get the set like set minus 9, minus 6, minus 3, etc. That is multiplying all the integers by 3 or the multiples of 3. That's equal to 3z. Similarly, cyclic 6 is equal to 6, etc. So these are all cyclic subgroup of the set of all integers under addition. Generally, we can say if we take any integer n belongs to z, then cyclic n is equal to the set etc. comma minus 3n minus 2n minus n 0 n 2n 3n etc. is a cyclic subgroup. Here all the subgroups are cyclic subgroups are infinite order, which contain infinite number of elements, but only one subgroup, that is the cyclic 0, is finite. Which means if we consider an infinite group, we get cyclic subgroup of infinite order. Cyclic group. An element A of a group G generates G and is a generator of G if cyclic A is equal to A raised to n is an integer that's equal to G. A group is said to be cyclic if it is capable of being generated by a single element A of the group. So a cyclic group is just like a cyclic subgroup, but here the group itself is a cyclic group and which is capable of generated by a single element. In the previous example, example number 1, Z6 is equal to 0, 1, 2, 3, 4, 5. This group itself is a cyclic subgroup because while we are going through the cyclic subgroups, cyclic 0, 1, 2, 3, etc., we can see that cyclic 1 is equal to Z6 and cyclic 5 is equal to Z6. Therefore, here 1 and 5 are the generator of Z6 and the group Z6 is cyclic. If the cyclic group A is finite, then the order of the smallest positive integer m such that A raised to m is equal to E. In this case, we write order of A is equal to m. So in the previous example, that is Z6 plus comma under addition modulo 6, the group itself is a cyclic group and this is of finite order and the order of the group is 6. If we take any element A from Z6, then A raised to 6 is equal to identity 0 under addition modulo 6. And if the cyclic group A is infinite, then A is of infinite order. For example, if we consider the group G is equal to set of all 1 omega omega square. Omega raised to n means the nth roots of unity and omega raised to n is defined by cos 2 pi by n plus I sin 2 pi by n. Here cube root of unity. So here we consider 1 omega omega square, that is omega cube is equal to 1. Here omega is equal to cos 2 pi by 3 plus I sin 2 pi by 3. Here G is equal to 1 omega square is generated by omega and omega square. That is G is equal to cyclic omega. G also is equal to cyclic omega square. That is omega and omega square are generators of G. There. Okay. In example number 2, the group Z6 is equal to 0, 1, 2, 3, 4, 5 under addition modulo 6 is a cyclic group. Already we discussed. Example 3, if G is equal to 1 minus 1 I minus I is a group with respect to multiplication. In the previous module, we also discussed about this group, and one of the subgroup of this group is 1 minus I. Okay, this group itself is a cyclic group because since G is equal to minus I square is equal to minus I into minus I, that's equal to minus 1, and minus I cube, that's equal to minus I into minus I, that's equal to minus I. Minus I raised to 4 is equal to 1. So every element of G can be written as a power of minus I. Therefore, minus I is the generator of G. Therefore, G is cyclic. In example 4, for any n belongs to Z plus, UN be the multiplicative group of nth roots of unity. In example 1, we discuss about cube root of unity. Here we are generalizing. Then UN be the nth root set of all nth roots of unity. Then UN is equal to omega n square, omega n cube, etc. omega n raised to n, where omega n is equal to 2 pi by n plus I sin 2 pi by n. Then UN generated by omega n. Therefore, UN is a cyclic group. So thank you for watching this video. This is the end of part 1 of module 2. In the upcoming session, we will be discuss about some properties and theorem related to cyclic group.